Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 2059, Bernhard Riemann submitted a relatively short paper to the Berlin Academy titled On the Number of Prime Numbers Below a Given Magnitude. This work, although concise, proved revolutionary, forever altering the course of number theory and leaving behind a legacy that continues to challenge and inspire mathematicians. Riemann's paper confronted the long-standing problem of understanding the distribution of prime numbers. Prior to Riemann's contribution, mathematicians had made some progress. The prime number theorem, conjectured by Gauss and Legendre, provided an asymptotic estimate for the number of primes less than a given number. This theorem, however, offered an approximate solution. It lacked the precision to determine the exact number of primes, or to predict their distribution with certainty. Existing methods fell short of providing a cohesive framework for understanding the seemingly chaotic arrangement of these fundamental building blocks of integers. Riemann's approach was radically different. He introduced the zeta function, denoted as zeta of s, initially defined for real numbers greater than 1 as the infinite sum of 1 over n to the s, where n ranges from 1 to infinity. Euler had previously established a crucial link between the zeta function and prime numbers with the Euler product formula. This formula states that the zeta function could also be expressed as an infinite product over all prime numbers p in the form of 1 over 1 minus p to the power of negative s. This connected a seemingly abstract function to the fundamental distribution of primes. The true stroke of genius lay in Riemann's decision to extend the zeta function to the complex plane. The initial definition, valid only for real numbers exceeding 1, became inadequate for a deeper analysis. Riemann demonstrated that the zeta function could be then analytically continued to all complex numbers, excluding s equals 1, where it has a simple pole. This analytic continuation is achieved through various techniques, such as Dirichlet eta function. This is defined as the alternating sum of 1 over n to the s, which converges for complex numbers with real part greater than 0 and can be analytically continued to the entire complex plane. Riemann then used this function to derive an analytic continuation for the zeta function. The act of analytically continuing the zeta function was essential. Extending the domain allowed him to apply the powerful tools of complex analysis to study its properties. The location of the zeros, or the complex numbers for which the zeta function equals 0, became the focal point of his investigation. Riemann recognized that these zeros held the key to unlocking the secrets of prime number distribution. Riemann established a functional equation that relates the value of the zeta function at s to its value at 1 minus s. This equation displays a profound symmetry in the complex plane. It implies that if s is a zero of the zeta function, so does 1 minus s. This functional equation represents a bridge connecting distant regions of the complex plane and providing vital information about the zeta function's behavior. Specifically, the functional equation possesses the form zeta of s equals 2 to the s times pi to the power of s minus 1 times sine of pi s over 2 times gamma of 1 minus s times zeta of 1 minus s, where gamma denotes the gamma function. Riemann identified two types of zeros: trivial zeros, which occur at negative even integers, and non-trivial zeros, lying within the critical strip, that is the region of complex numbers with real part between 0 and 1. He conjectured that all non-trivial zeros have a real part equal to 1 of. This became known as the Riemann Hypothesis. This seemingly simple statement constitutes one of the most significant, unsolved problems in mathematics. Should the Riemann Hypothesis prove true, it would provide the sharpest possible bounds on the distribution of prime numbers. Riemann also introduced the Riemann xi function, denoted as xi of z, as a modified version of the zeta function. This function exhibits simpler symmetry properties, making it easier to work within certain contexts. The xi function is defined such that its zeros coincide with the non-trivial zeros of the zeta function. Central to Riemann's work is what is now referred to as the Riemann explicit formula. This formula expresses the prime counting function, denoted as pi of x, which gives the number of prime numbers less than or equal to x, in terms of a sum involving the logarithmic integral function, denoted as li of x, and a sum over the non-trivial zeros of the zeta function. The logarithmic integral function provides an estimate for the number of primes up to x, refined by the contribution of the zeta function zeros. The explicit formula, though not rigorously proved by Riemann in his original paper, provided a concrete connection between the zeros of the zeta function and the distribution of prime numbers. It suggests that the oscillations in the distribution of primes are directly governed by the location of these complex zeros. The precise relationship, though complex, offered a tangible pathway toward understanding the seemingly random nature of prime numbers. Euler's work on the zeta function and its connection to prime numbers provided the foundation upon which Riemann built. Gauss' conjecture regarding the density of prime numbers, expressed through the logarithmic integral, served as another crucial influence. Dirichlet functions, generalizations of the zeta function, also offered inspiration. Chebyshev's earlier work on prime number distribution also contributed to Riemann's thinking. Riemann's 1859 paper, despite its brevity and some unproven claims, had a profound impact on the field of number theory. It provided a new analytical framework for understanding prime numbers. It introduced the complex zeta function as a central object of study. The prime number theorem was proven independently by Hadamard and de la Vallée-Poussin using Riemann's insights, specifically by demonstrating that the zeta function possesses zero zeros with a real part of 1. Von Mangold later provided a rigorous proof of Riemann's explicit formula. The quest to prove or disprove the Riemann hypothesis has driven research in analytic number theory for over a century. Hilbert included it as one of his 23 problems. The study of the zeta function and its generalizations continues to be a vibrant area of research in mathematics and physics. Its methods and discoveries have far-reaching implications across multiple scientific and technical disciplines. Riemann's seminal 1859 paper on the number of prime numbers less than a given magnitude represented a paradigm shift in number theory, introducing complex analysis to the hitherto strictly integer domain of prime number distribution. The paper's power lies in its partially conjectural introduction of the Riemann zeta function into prime number theory, revealing a deep connection between the distribution of primes and the location of the zeros of this complex function. Riemann presented an explicit formula linking the prime-counting function, denoted pi of x, to a sum involving the logarithmic integral function, symbolized as lie of x, and a summation across the non-trivial zeros of the zeta function. This explicit formula, initially asserted without a complete proof, provides a method for approximating pi of x with increasing accuracy. Riemann's formula is a potent tool in analytically approximating the number of primes below a given threshold. Critically, the formula necessitates the analytic continuation of the zeta function, initially defined only for complex numbers with a real part exceeding 1, to the entire complex plane, excluding the point 1. This analytic continuation is achieved via an integral representation, a technique of significant independent interest. Riemann's paper contained a conjecture that proved especially impactful: the celebrated Riemann hypothesis. This hypothesis posits that all non-trivial zeros of the zeta function lie on the critical line, possessing a real part equal to 1/2. Should this hypothesis hold true, it would provide the tightest possible bounds on the distribution of prime numbers, significantly refining our understanding of their seemingly erratic appearance. It proposes a level of order within the prime number distribution far exceeding what was previously suspected. Proofs of several elements initially presented by Riemann emerged subsequently. Hadamard and de la Vallée-Poussin, building upon Riemann's insights, independently proved the prime number theorem. They demonstrated that the zeta function has zero zeros with a real part of 1. This proof solidified the asymptotic distribution of primes, affirming that the number of primes less than x approaches x divided by the natural logarithm of x as x tends towards infinity. Furthermore, von Mangold supplied a rigorous and complete proof of Riemann's explicit formula, solidifying its place as a cornerstone of analytic number theory. His work provided the analytical justification for Riemann's initial assertions. The core of Riemann's approach lies in the utilization of complex analysis. It allows for an analytical attack on a problem that, at first glance, appears purely combinatorial. The explicit formula embodies this, intertwining the discrete nature of primes with the continuous world of complex functions. The beauty of the zeta function stems partly from its expression as an infinite product over primes, known as the Euler product formula. This formula provided an early connection between the zeta function and prime numbers, directly influencing Riemann's thinking. The explicit formula showcases the ingenuity of complex analysis. An example of its use involves evaluating the logarithmic integral function, lie of x, which provides an approximation of the number of primes less than x. The summation over the zeros of the zeta function refines this approximation, accounting for the oscillations in the prime distribution. The better we understand the location of these zeros, the more precise our estimate of pi of x becomes. The influence of Riemann's work extends far beyond the immediate results concerning prime number distribution. His paper spurred the development of analytic number theory as a distinct and flourishing field. The Riemann hypothesis occupies a central place in mathematics, its resolution promising profound rewards. Hilbert included its proof as the 8th of his 23 problems presented at the International Congress of Mathematicians in 1900. Despite extensive efforts, The Riemann hypothesis remains unproven in the present day. Mathematicians have verified the conjecture for billions of zeros, and ongoing computational verifications continue to extend this range, bolstering confidence in its truth. The failure to find a counterexample, however, does not constitute a proof. Moreover, the search for a proof has led to the development of many powerful techniques and insights in complex analysis and number theory. Mathematicians have extensively expanded the study of zeta functions and L functions, generalizations of Riemann's original zeta function, with applications in various areas of number theory. Dirichlet's L functions, which generalize the zeta function, incorporate in Dirichlet characters, also influenced Riemann's investigations. These L functions are employed in the study of arithmetic progressions of primes. The ongoing quest to understand the Riemann hypothesis and its generalizations is a testament to the enduring power and significance of Riemann's 1859 paper. It continues to be foundational in number theory and relevant to current research.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.